Hello everyone, welcome to Recycle Guy. Today I'm going to show you how to prove the rotational inertia of a solid sphere with the rotation axis going through the center of the sphere. I know there are some proofs out there on the internet, but I didn't find one proof using spherical coordinates. So today I'm going to show you how to use this calculus method to calculate the inertia. So the first step would be just to lay out the definition of the rotation inertia. And then we need to look into what is R and what is dm. So bear with me the bad drawing here. But basically what I want to illustrate is, you see the big circle here? This stands for the solid sphere. So let's first look into dm. Because we assume that the mass is evenly distributed inside the sphere. So we know that any small particle dm over the mass of this sphere would be just the ratio of the corresponding volume here. And then we could deduce that dm equals capital M over capital V times dV. Now we need to look into what is dV. Okay, so to find out dV, we need to use the spherical coordinates, which has three parameters: phi, theta, and rho. So phi is the angle from the destination line to z-axis. So it ranges from 0 to pi. Theta is the angle between the terminal side to the positive x-axis. And rho is the destination point to the center of the sphere, the distance. So rho could range from 0, which is right at the center of the sphere, to r, which is the radius of the sphere. I believe, by the way, I believe that in your calculus textbook, specifically it should be calculus 2, you would find a much better graph of this illustration, and this is called a wedge in the textbook. So now let's find out the volume of this dV. So speaking of the volume, we need to find the length, the height, and the width. So the length here would be this length, which is rho, times this angle, which would be dphi. So rho times dphi times, so this is the height. The height would be just d rho here, right? Because this is the rho, so this is just a tiny bit of d rho. So times d rho, and then the width of the wedge, we need to look into the projection of this wedge on xy plane. So I believe the width equals to this tiny arc, and we know how to find out the length of this arc, which is the side times the angle here. Okay, the side would be rho times sine phi. right? Just look at, let's say this is our rho. So sine phi would be this side. And that's exactly the projection on xy plane. So which is rho sine phi. And then we need to multiply it by the angle in between, which is d theta. So we got, there are several items we could combine together. Here is rho squared and the sine phi times d rho, d phi, and d theta. So d rho, d phi, and d theta. So this is our dv. Later on, you could always go back to your textbook to see the same process. Okay, we found the dv. Now let's look at, so this is, we just analyzed the dv here, dm here, but we also need to look into r. Remember, r is the distance between the particle to the rotational axis. So it's this distance. And this distance is rho sine phi. So we know that r equals to rho sine phi. Okay, so let's substitute these two items that we just found into the rotational inertia equation here. So rho sine phi squared times m over v times dv. So m and v, they are constants, so we could take them out of the integral. And dv is what we just deduced, which is rho squared times sine phi d rho d theta d phi. And next, because it's a sphere, so theta ranges from 0 to 2 pi, phi ranges from 0 to pi, and rho ranges from 0 to r. Okay, so I believe we found out all of the ranges of our parameters. So after we doing some combine those terms, we found it's rho to the fourth times sine phi to the third. And then just next few steps, just just to do the calculation, and you will find out the same answer as the textbook. Okay, I hope you like this method, because at least it gives you another way to think about the proof. Hope you like it. Thank you for watching.